Hello and welcome to another World Cement Spotlight. My name is David Bisley, Senior Editor of World Cement, and I'm delighted to be joined once again by Mr. Hans Conrads, Managing Director of PROMECON. And today we're going to be talking about the importance of accurate and reliable measurement of tertiary air. Hans, thank you so much for joining me for this Spotlight interview. Great to have you with us once again.
Well, thank you very much and happy to be here. Thanks for having me on.
So, with so many different things that plant managers have to worry about, why is the management of tertiary air of such key importance?
Tertiary air has been introduced a couple of decades ago. Before, you just had one rotary kiln going from the clinker cooler to the preheater tower. With the introduction of tertiary air, it came along that you could basically outsource the pre-calcining from the kiln to the preheater tower, the bottom of the preheater tower. So that would allow spreading out the heat much better, making the process far more efficient, and also lower NOx significantly. So the introduction of tertiary air was really a little revolution in making plants far more environmental friendly and also using less energy. Now, the tertiary air runs parallel to the rotary kiln, so it is connected basically to the rotary kiln on one end, the clinker cooler. They both come off the clinker cooler. And on the other end, they're also connected because they're both running, the gas flow runs into the pre-calciner. So you have two branches of massive airflows or process gas flows that go parallel, and managing these is quite pivotal. The balance between tertiary air and secondary air through the rotary kiln is very, very important in order for the NOx reduction, but also for the oxygen content on the kiln inlet. And all this needs to be tightly controlled. And if it is not controlled tightly, then usually operators run on a more safe side, for example, for product quality, for stoichiometry in the kiln. But that means that tertiary air can be way over or way under, and that has consequences for the process later on. It has consequences for the pre-calcining. It has consequences for the power consumption of the ID fan and for the stability of the whole process. So tertiary air is not just a sideline, it's pretty central to the whole pyro process, and it needs to be balanced and handled correctly.
Now, obviously, every cement plant is different, but can you give us a rough idea of the difference in terms of costs or efficiency between a cement plant that has effectively managed its tertiary air and one that has failed to do so?
Yes, I would like to point out a couple of aspects that you should consider. And these aspects all are tied to a lot of energy consumption and money. And so instead of pointing out a number, so many $1 million per year or something, I would just like to make the listeners to the interview aware of the issues that they have. The first one, of course, is always fan power. When you're drafting gas flows, and the gas flows through the main kiln and the TAD are massive gas flows, the ID fan is a big fan. You certainly do not want the ID fan to run over its necessary capacity. Most of the modern ID fans have VFDs, so variable frequency drives, and that means that the power consumption of the ID fan rises with the flow to the third order. So if you're a little bit over, a little bit on the high side, it means that you're using massively more electricity. So you would like to cut that back, and if the flow through your main kiln is correct, you also would like to have correct flow through your TAD, so the total flow is correct. And if you look at numbers, ID fans typically they can be half a megawatt, they can be 1 megawatt. They're big fans and they use a lot of energy. And if you can save 10% or 20% or 15%, then you can calculate easily the savings. Another aspect that is not about drawing too much gas, but is simply stability of a process. And this aspect is that since the relation between gas flow and power consumption is nonlinear, any oscillation up and down goes around the 0 point when it comes to flow, but it does not go around the 0 point when it comes to electricity. because the high side uses far more electricity than the low side saves you. So you would definitely, just for energy consumption issues, you would like to run your process as flat as possible. And the same thing, of course, applies to all the things, O2, product quality, the consistency of the pyro process. These have big impacts also on fuel consumption and on many other aspects of product quality. So managing tertiary air also is not about saving process gas energy, but also saving or flattening the process itself to have less losses on product quality and overall fuel consumption. The tertiary air was also a big advancement in reducing NOx in the process. Because you had a pre-calcining process and you could do the pre-calcining before the kill. But if your tertiary air is too much, because tertiary air is the main source of oxidation in your pre-calciner. You have fuel and you have oxygen that you add in your pre-calciner. And that oxygen mainly comes from TAD. So what if your TAD is too high? What if your temperatures in the pre-calciner are not uniform, or if you have too much on tertiary air go into your pre-calciner? You will produce huge amount of NOx again. And this NOx is another thing. It is mitigated usually by injecting ammonia, and we all know the ammonia costs $300, $400, $500 per ton of ammonia. So cutting back on ammonia because you have a lower primary NOx in your pre-calciner is a huge saving again. We're talking not small numbers, we're talking big numbers here as well. So these are a couple of the typical aspects of operational that you get by a better tertiary air flow management.
Okay. So regarding that management process then, what are the typical problems or challenges encountered when it comes to sort of gas flow measurement in the TAD, and why do measurement systems typically fail?
Well, the TAD is a duct that is usually completely lined with refractory, because the tertiary air comes directly from the clinker cooler hot zone. Tertiary air is around 1,000 degrees Celsius. It carries huge amount of clinker dust, which is very abrasive. So now you have hot gas, high velocity, abrasive clinker dust. All this doesn't sound very nice for measurement. These are the typical ingredients for measurements to fail due to mechanical impact, due to thermal impact. And that's the reason why we have specialized on process gas measurement, because all these issues always happen in process gas. Now, in tertiary air, it is extreme because you have also the highly abrasive clinker dust being transported with it. And that's basically it. If you have typical measurements to measure gas flow, you would think of a Venturi. You would have to build a Venturi into the tertiary air duct. Some people do that, quite difficult. Also here, a lot of abrasion. You could stick something into the Venturi, like a pitot tube. It will probably only last for a few hours. We have successfully installed tertiary air measurements with our triboelectric systems, but also these do not last forever. We have highly abrasive material, which is cutting down the antennas of our sensors. So the way that we have to think about is going around all these obstacles, all these problems, to get a measurement that is drift stable and that is also lasting for quite some time. And that is important first step to regulating tertiary air gas flow successfully.
So what exactly then is PROMECON's solution to navigating this variety of challenges?
The main solution now that we have introduced into the market with all our experience on other lower temperature process gases is we are sticking to our very successful cross-correlation principle, which is digital and gives you a drift-free signal. However, we have moved the whole thing out of the process. We are now offering a infrared solution, which is looking into the duct from the outside through two holes. And we're cross-correlating basically the light emission coming from the tertiary air gas. And that means that our system is not in contact with the process anymore. So we're just looking from the outside, and that is actually the key to a maintenance-free, abrasion-free, drift-free measurement.
Let's go into a bit more detail about this infrared system then, the McON IR. What are some of its unique features? What makes it so well suited to operating in the TAD?
Actually, the heritage of the system is really from all our other systems that we have been putting into the market since 2000. Our first cement installation was in the year 2000. And we have learned how to interpret the correlation signals so that we have a very reliable, stable signal. So that is the old part that has not changed much. We have algorithms that can detect very well the significance of the correlation, and we can filter out any unknown or unwanted parts or noise from that. I think we're the only company in the world that has provided CO2 compatible correlation-based measurement that would work for years without dropping out. The new part and the exclusive part here is to combine that with the infrared emission from the duct. Our measurement has infrared diodes, which are fast enough and responsive enough to see the fluctuation of the infrared light good enough so that we can have a very clean and very reliable signal. So the combination of infrared with our very advanced cross-correlation processing technique is what makes this system unique and also very robust in long term.
So, what is the installation process like? How long does it typically take, and what kind of impact, if any, is there on plant operations during the installation?
Right. What we need is 2 access holes to the tertiary air duct. And usually in the cement plant, putting 2 holes in the duct is not a big deal. In the tertiary air duct, it's a bit more of a work because you would also have to drill through the refractory. So this usually has to be done when the plant has a shutdown, and you can do this work safely. And then you have to weld on a couple of mounting adapters that allow the system to be inserted into the duct. And that's it. You have cables then that go to the box. From the box, if the box needs a power supply, and from the box you have a 4 to 20 milliamp signal going back to the DCS of a plant. So the integration into the plant itself is fairly simple. And you can use the signal directly to control dampers, or you control your fan with that. So that's basically what we have to do. Putting 2 holes and putting the adapters in. We also recommend to add some purge air to keep everything clean from dust. But this requirement also with the infrared has come down quite a bit. There's not much purging requirement anymore. The system is really well suited for this really special type of environment.
And how many units would a plant generally need installed?
Well, the plant usually needs 1 TAD, and it needs 1 unit. It's not a bad question, because on a downcomer or on other gigantic ducts, or where you don't have such a long straight run, you might want to measure at various points over the cross-sectional area because you have some flow stratification. If you have, for example, a raw mill outlet, it might be necessary to measure out at several locations at the same time and average that so you get a meaningful result. In TADs, usually that's not necessary. We just go to the middle of the TAD. We have a very long straight run. So we have a flat profile without stratification. Sometimes TADs also have venturis built into them out of refractory. The shallow section of the venturi is always the best location because there you have the biggest flow straightening effect. But even without that, it is very easy to achieve a reliable and accurate signal with one system.
Okay, and what are the maintenance requirements typically like, and what sort of operational limits are there for the system? Maximum temperatures, things like that.
Look at the system once that you have your plant down every year or every 1.5 years. Take a look at it. The cables are all correct. The holes are fine. As long as the system doesn't drop out, there's absolutely no reason to do anything on the system. As mentioned, the system is completely digital. It has no drift whatsoever. It has no 0 point because it measures the time of flight between sensor 1 and sensor 2. And if the gas velocity is 0, that time becomes infinite. So there is no 0 point like on a delta P device that you have to frequently check. There's nothing that you would have to check in terms of dirt on the sensors because there's no sensor inside the process. And even if we had one, the dirt would not matter. Like on a anemometer, hot wire anemometer or something. So basically, there is nothing that you will have to check in order to keep the system. Also, keeping the hole clean from dust, like on a typical acoustic system, a time of flight system, ultrasonic or anything like that, is not necessary. If you see our reading, the reading will be accurate, and we would anticipate that the system will run for many years. Still, we recommend, once the plant is down, you're checking through all the instrumentation, do us a favor, have a look. Sometimes cable is snapped or something happened. The outage, when people come back, the system doesn't work anymore. It's usually very simple things, and therefore no regular maintenance. But sometimes we have some operators that don't know where our systems are. We've been to plants and they told us, we don't know where your system is. We just see the value. But I've only been here for 5 years. I've never seen it. So that should not happen. Once in a while, you should.
Okay, great. Now, in addition to the benefit of more stable, efficient operations, which of course is a huge benefit, what other benefits can cement producers expect to receive from effectively managing their tertiary air with this kind of system?
I think another big topic we haven't talked about is downtime. Tertiary air has a big impact on the temperature distribution on the kiln inlet section, but also the preheater tower. And besides the NOx formation that you have, you can also have formation of buildup. You can have sulfur bicarbonate buildup in big chunks, and this has usually to do with temperature profiles, with certain gas recirculation. And the way you can only manage that is changing your temperature distribution, changing your gas flows. Now, in many plants, people don't know their gas flows. Still, even though we have been in the cement area now for 20, 25 years, still many plants have no real clue of what their gas flows are. There are theoretical calculations when you design the plant, and once it's running, it's more or less a repair shop, and you just live with what you have. But having a better management on your gas flows can substantially reduce problems like buildup, and that would reduce downtimes. And downtimes, how do you calculate the benefit of that? Beside the work and the labor, of course, capacity loss of your plant. Depending on the pricing level of the market, it can be very substantial to have downtimes that you don't want to have. So that's, I think, another very big aspect of managing your tertiary air correctly.
Right. So before we draw things to a close then today, do you have any final thoughts for our audience?
We have been contacted by a couple of big cement makers in light of the new perspective of low carbon cement, zero carbon cement. This whole thing means a transition in the cement making process. Depending on what kind of process will come in the future, you still might have TADs or you might not. It depends. But what you would certainly have is a much, much better management of your gas flows. Because now that you are really looking at the gas constituents themselves, mainly the CO2, and how much CO2 enrichment do you want to have before you sequester the CO2 and you put it out into a different part of the plant, you would really have to manage gas flows. You'd have to manage CO2 flows. We have several inquiries for measuring gas to a very, very high accuracy level, because now CO2 becomes a cost factor that's traded over a trade point. But also inside the process, it would be very important to have better knowledge of moving gas around, because never forget, the gas is a huge cost factor in making cement. Moving the gas around, transporting the thermal efficiency, but now also having the gas as a cost factor that you need to get rid of. All these, I think, will trigger more knowledge about the process. And we don't know where it's going to happen in the future. We are welcoming any large cement maker and producer to contact us if they have problems or have their own ideas of what they want to look at in the future. It is really our specialty to look into process gas, and the harder it is, the more inspired we are, because that's what we are. We are the process gas company.
Okay, well, Hans, thank you so much for joining us once again and sharing your experience with our audience. And as always, a huge thank you must go to you guys in the World Cement audience. Thank you for your continued support. If you'd like to find out more about PROMECON and the services they provide, simply head over to www.promecon.com. Thank you and goodbye for now.